Hi, my name is Abdulaziz from Hurriyat University. In this presentation, I'm going to present our work about blind deconvolution of images corrupted by Gaussian noise using expectation propagation. The blind image deconvolution problem arises in many applications such as commercial photography, remote sensing, microscopy, and many other applications, where images can be degraded during the observation process by blur, noise, and other degradations due to imperfections in the sensing system. Since these degradations are unknown in practice, blind image deconvolution technique seeks to recover the sharp image without knowing the blur in advance, which leads to one of the most challenging problems in the image processing community. The image degradation model for linear shift invariant blurring effects can be written as a convolution process between the original sharp image and the blur kernel whose support is assumed small compared to the image size. Equivalently, the convolution process can be written as a multiplication between a block circulant matrix constructed from the kernel edge and the original sharp image. The observations are also corrupted with an additive Gaussian noise with known variance sigma square. In this context, the BID problem is severely ill-posed inverse problem in the sense that an infinite set of x and h can explain the observed data. Hence, prior information about both the original image and the blur kernel are needed to discard unwanted solutions. The BID problem consists of inferring the original image and the blur kernel given the blurred image. In a Bayesian framework, the observation model defined the likelihood term. Moreover, since the BID problem is severely ill-posed, Bayesian methods incorporate prior information about the original image and the blur as prior distributions. And the joint distribution of inferring the image and the blur is a multiplication of the likelihood term and the prior distributions. Many image prior models have been adopted in the BID literature, such as Gaussian priors to promote smoothness or sparsity-inducing priors. In this work, we adopt a combination of two priors as an image prior model. The first is the L1 norm-based total variation prior, which promotes piecewise constant images and is a popular example of Markov random fields prior. TV was frequently used in the PID literature in the aim to preserve edges while reducing noise in flat regions. And we define it as the sum of the modulus of the horizontal and vertical first-order differences corresponding to the left and top neighbors of a certain pixel. The second image prior we adopt to satisfy the physical constraints is the indicator function of the image non-negativity. As a blur prior model, we use in this work non-negativity and unit norm constraints. These constraints have shown to give good estimate of the blur, given the fact that usually the blur support is much smaller than the image size. Different estimation strategies can be used to infer the original image and the blur given the observations. Stochastic sampling methods, such as Markov chain Monte Carlo, generate a sequence of samples from the joint probability distributions. And then, these samples are used to approximate the joint minimum mean square error estimator of both the image and the blur. These methods usually require many samples to accurately explore the posterior distribution, which make them very intensive for high-dimensional problems. Another approach is a joint maximum a posteriori estimator of the image and the blur. The approach consists of maximizing the posterior distribution with respect to each unknown while holding the other one fixed. This approach is computationally very efficient, but don't allow uncertainty quantification for assessing the reliability of the estimated solution. The third approach, which is adopted in this work, is based on the expectation maximization algorithm. It consists of estimating the blur kernel via marginal maximum a posteriori estimation And then the estimated blur is used to estimate the original image via conditional MMSC estimation. The main limitation of the traditional EM algorithm is that the conditional probability distribution of the image given the observed data and the kernel parameters is usually intractable. The standard EM algorithm consists of two main steps, the expectation step and the maximization step, and these two steps are repeated until convergence. However, in many cases, the standard EM algorithm cannot be applied directly because the expectation involved in the E step is intractable. To overcome this problem, an approximate Bayesian method can be used to replace the intractable conditional distribution by a tractable approximate distribution, which is usually Gaussian, which make the expectation tractable. The resulting EM algorithm leads to the steps presented in the green box. In this slide, we compare between the different approximate Bayesian methods that can be used to replace the intractable probability distribution involved in the E step of the EM algorithm. We mainly compare between the variational bias algorithm that is widely used in the literature and the expectation propagation algorithm that is adopted in this work. Approximate Bayesian methods minimizes the alpha divergence between the true distribution and the approximate distribution. When alpha equals 0, we have the variational bias algorithm, which minimizes the KL divergence between the approximate and the true distribution. And when alpha equals 1, we have the expectation propagation algorithm that minimizes the reverse KL divergence between the true distribution and the approximate distribution. It turns out that when alpha tends to minus infinity, the algorithm prefers matching one mode, while when alpha tends to infinity, the algorithm prefers covering the entire distribution. This makes the EP approximation closer to the true distribution. Moreover, EP is easy to parallelize and very fast when implemented properly, and it provides accurate estimates and uncertainty maps. In this work, we adopt the EP algorithm to approximate the conditional probability distribution involved in the E step of the EM algorithm by a simpler Gaussian distribution. By using the block formulation of EP, the joint probability distribution can be factorized into three different factors, where the first factor represents the likelihood, the second represents the TV prior, and the third represents the non-negativity constraint. EP approximates each factor by a simpler Gaussian distribution such that the EP approximation is the product of all the approximation factors. And at each iteration of EP, all approximation factors are refined sequentially by matching the moments of the tilted distribution for each approximation factor to the EP approximation, where the tilted distribution for factor I is the product of that factor by the ith cavity distribution. And the ith cavity distribution is the product of all but the ith approximation factor. In this work, we use an attractive implementation of EP by considering diagonal approximate covariance matrices while moment matching. The bottleneck of EP arises during the update of the likelihood approximation factor, when matching the moments of the tilted distribution and the EP approximation. The updated marginal variance is given by the diagonal of the covariance matrix Cx tilde. This update required the costly inversion of the matrix Cx to the power minus 1. This inversion problem is common in all Bayesian approximation methods such as VB. In addition, the covariance matrix Cx tilde is used to compute the matrix Dx, which is required in the M step of the EM algorithm. Different strategies can be adopted to compute the covariance matrix Cx tilde. In the first strategy, Cx tilde is a full matrix computed as the direct inverse of Cx to the power of minus 1. In the second strategy, Cx tilde is a diagonal matrix whose diagonal is the inverse of the diagonal values of Cx to the power minus 1. In the third strategy, Cx tilde is a diagonal matrix whose diagonal is approximated using an efficient covariance approximation method dubbed Rho-Blackwell's Monte Carlo. Even if we run EP with a certain approximation strategy to compute Cx tilde, We can still at the end of EP use another strategy to approximate the matrix Cx tilde used to compute the matrix Dx. This allows running EP with a certain covariance approximation while estimating the kernel with a different covariance approximation. And the same applies for VP. In the table, we present the adopted acronyms of the different computation and approximation strategies for the covariance matrices Cx tilde and Dx. We showcase the performance of the proposed approach on simulations utilizing the cameraman image with a peak value normalized to 1. The original image is degraded with a linear motion blur and corrupted with IID Gaussian noise corresponding to SNR equal to 20 dB. The regularization parameter associated with the TV prior in all the methods is set to lambda equals 6.7. We start by evaluating the performance of EP in terms of reconstruction quality and computational time, assuming the kernel is known. EP with TV prior and non-negativity constraint is compared to EP and VP with TV prior alone. We also report the results of the proximal MCMC algorithm with TV prior and non-negativity constraint and with TV prior alone. The figure displays the MMSC estimators obtained by the different methods with image size equal to 128 square pixels. The figure clearly shows comparable mean images for all the methods. Interestingly, the images of marginal variances of EP are very close to those obtained with MCMC, confirming the improved reliability of the estimated variances of EP over VP here. In addition, the computational time of EP is around 4 orders of magnitude slower than that for MCMC. We also noted that VP seems to underestimate the variance. Finally, incorporating the non-negativity constraint in the prior image model tends to decrease the uncertainty in the low-intensity regions. We now assess the performance of EP when the kernel is unknown. The proposed PID approach, EPEM with TV prior and non-negativity, and with only TV prior, is compared to VPEM with TV prior. The tests are carried out with different image sizes from 64 square to 512 square. The figure showed the image PSNR and compute time corresponding to running the methods with the different covariance computation strategies explained earlier. The first row suggests a comparable computational time between EPEM with TV and non-negativity and VPEM with TV for all strategies, while EPEM with TV takes more time to converge in some scenarios. The second row suggests that running EP and VP with fast CX tilde and RPMC CX tilde gives PSNR values very close to those obtained when running with expensive CX tilde. However, the computational time can be drastically reduced. Finally, we noted that both EPEM with TV and non-negativity and EPEM with TV alone maintain better PSNR scores around 1 dB enhancement for all image sizes. To conclude, we have presented a blind deconvolution method leveraging the EP algorithm within the EM framework, as opposed to other work in the literature where the variational bias algorithm was deployed to approximate the intractable E-step of the EM algorithm. We proposed to use the EP algorithm as a better approximation method. We showcased on simulation that the proposed EP-EM algorithm can provide better supervised and blind deconvolution results reflected by higher PSNR and more reliable uncertainty maps than VPEM for a comparable computational time when using the same original model. In a future work, we'll include a more detailed analysis of the EPEM algorithm for different blur sizes and more complex image prior models. And thank you.